Project 1.3, a counting circuit. This project is divided into 9 parts, A to I. In short, the counting circuit is a circuit designed to track and display numbers through a sequence of connected digital components. At its core, the circuit receives input signals that initiate the counting process, generates a clock signal comprising of pulses with defined duration and frequency, and ultimately presents the count on a display. The button input provides power to the next stage in the circuit, the NAND gate oscillator, and serves as the input to start the counting sequence in the final counting circuit. The button input is made of the parts listed on screen. The pull-up resistor keeps the LED high at rest, and pressing the button pulls it low. The pull-down resistor keeps the LED low at rest, and pressing the button pulls it high. The counting circuit uses the pull-up resistor configuration. The purpose of the NGO is to provide a clock signal used by the next stage in the circuit, the decade counter. The clock pulses produced have both a duration and frequency. At its core, the NGO runs off NAND gates and 2 resistor capacitor networks. Capacitors charge and discharge based on resistor values. With the 9-volt power source, the NAND chip considers inputs below 4.5 volts as low and above 4.5 volts as high. This converts analog inputs into digital square wave outputs, creating the clock signal. The LED blinks to indicate the frequency. The NGO has 2 RC networks. RC1 controls the frequency and RC2 controls the capacitor's charge and discharge time, affecting the clock signal. The capacitors store and release energy after reaching 4.5 volts. Using a larger capacitor or resistor extends the signal's duration and frequency. I added a potentiometer to RC2 to adjust the clock frequency and control the counting speed for the final build. The decade counter's purpose is to take the NGO's clock signal and divide it into 10 intervals throughout the IC's output gates. This division is shown on an LED bar graph. This circuit uses the 417 decade counter IC. Output pins Q0 to Q9 are wired to the segments of the LED bar graph in sequential order. The IC generates sequential outputs based on the clock signal from the NGO. This allows the decade counter to count from 0 to 9 and display the count. After reaching 9, it resets to 0. The NGO's potentiometer adjusts the count speed. The divide by 10 pin powers an LED oscillating at 1/10 of the NGO's clock frequency. This pin provides the clock signal to the next stage, effectively slowing down the clock's frequency. This circuit counts in binary from 0000 to 1111, or in decimal 0 to 15, displayed on 4 LEDs. The 4516 IC drives this, taking the divided by 10 clock signal from the decade counter, meaning the potentiometer can adjust count speed. The clock signal provides binary coded decimal, or BCD, data, which the chip processes into output signals representing the current count in BCD format. These signals are then sent to the LEDs. The chip has 3 features. Firstly, reset. The pin is active low, and pressing a button triggers a high, resetting the circuit to 0. Secondly, up-down. Toggling the switch to power causes the circuit to count up, while ground causes it to count down. Finally, a preset function, which is explained later in Part I. Parts E and F complete the single-digit counting circuit. The BCD decoder processes data from the 4510, which is the same as the 4516 used in the last step, except it counts up to 10. It converts this data into input signals for the common cathode 7-segment display, lighting up certain segments which form decimal numbers. The frequency adjusting potentiometer, up-down switch, and a reset button still work. 3 new features are added. Firstly, the display test, which is toggling high, turns on all segments, showing 8. Secondly, the blank input, which toggling high, turns off the display. Thirdly, the store, which toggling low, stores the number internally. For all 3, the circuit continues counting internally. The single-digit counting circuit breadboard prototype is converted into a compact, practical version on an encased custom PCB, with these parts soldered on. A battery covered with electrical tape inside connects to a terminal block, powering the circuit. It functions exactly like the breadboard version, but uses a larger capacitor in RC1, making it count longer. This version still has an up-down switch, and now has a new on-off switch. However, it cannot be preset, reset, or use a display test, blank input, and store functions, and lacks adjustable speed. This circuit adds a tens digit to the counting system. The divide by 10 pin of the 417 is wired into the clock signal of a second 417. This causes the circuit to count at 1/10 of the speed of the ones digit, effectively forming a tens digit. From there, all build steps are repeated, finishing the circuit. Instead of adding a second button for each feature, the original button or switch is wired to the corresponding pin on the second set of chips. For example, the store switch is connected to both pin on both 4511s, so both digits are stored simultaneously when toggled. As mentioned earlier, a preset function is built using the 4510 ICs. Each input pin of both ICs is wired to a slide switch representing a binary value, with the preset pin connected to an active low button. The preset switch values are 8, 4, 2, and 1. To preset, for example, 96, set the tens digit to 9 and the ones digit to 6. Pressing the button will then display 96. If the value on the switches ever exceeds 9, so for example, 11, the display will turn off. I hope watching this video helped you understand the counting circuit. Thank you so much for watching.